Okay, students, I'm your physics teacher and my name is Theodros Gizau. Today we'll see grade 7 lesson 4, grade 9 lesson 4. It's about temperature and heat, and this one is the second lesson for unit 7. And in this section we'll see about expansion of solid, liquid and gases. And here, always, as we said, the substance gains heat energy, it will expand. That means its volume or size increases, and this expansion is treated by these three ways. The first one is expansion of solid, liquid and what? Gases, and we'll see separately each of them. And for the first, the expansion of solid, let us see expansion of solid, and we classify this expansion of solid into three. The first one is Length expansion, and the second one is areal expansion, and the third one is volume expansion. Therefore, for today we will see about length and areal expansion. Therefore, as we said, we can classify into three. And when a solid is heated, its particle moves further apart, causing the solid to expand. And the amount of expansion of solid depends on two things. And the first one is the nature of the solid and the amount of the rise of temperature. These are the two factors which determine in what level or in what manner the substance or the solid expands. And there are three types of expansion of solid. These are, the first one is linear expansion, the second one is areal, the third one is volume. Therefore, in this section we will see about the linear and the areal expansion. Let us start with linear expansion. In linear expansion, when a metal rod is heated, it expands and the increase in length, and this expansion is called linear expansion. And the diagram below, you'll see that in the diagram we have LC and LH. LC stands for before it's heated, and LH stands for after it is heated. And in this diagram, as we said, LC is before it's heated and LH is after it is heated. And LC in other way, it means that and the temperature is equivalent to 0 degree Celsius, and this one is when the temperature is what? The temperature is equivalent to hot. And here C stands for cold and H stands for hot. And this change in L is the change between the cold and the hotter length of the rod. And the rod temperature has increased by change in T. Therefore, change in T is equal to TH minus TC. That means temperature hot minus temperature cold. And change in L, as I said before, change in L is equivalent to LH minus LC. LH is length at hot and LC is length at cold. And this is written as change in L is equal to LH minus LC. And so far, an increase in temperature of change in T causes the fractional increase in length. When we say fractional increase is equal to change in L, that means increase in length divided by the original length of the wire, LC. For example, we'll see one example. If 50 centimeter rod expands by 2 centimeter, the fractional increase becomes is equal to change in L is how much? 2 centimeter divided by the original length of the rod is how much? 50 centimeter divided by 50 centimeter. This one becomes 1 over 25 centimeter is cancelled by 10 centimeter, and or this one in terms of 0.04 becomes 0.04. Therefore, the fractional increase is change in L over change in L over LC, and the fractional increase for this example, this one is the expander length and this one is the original length. Therefore, 2 over 50, and finally you got 1 over 25 over or 0.04. And the fractional increase in length per unit area, per unit temperature increase is given by the symbol alpha. Alpha is the linear expansion coefficient. Therefore, alpha is equivalent to change in L, this here alpha is equal to change in L over LC the whole over change in T, and over change in T we have 1, and when we invert, this one becomes change in L over LC times 1 over change in T, Therefore finally after rearrange you get after rearrange change in L over LC times change in T, because 1 is multiplied by change in L, you got change in L, and LC times change in T becomes LC change in T, and change in L over LC change in T is the final answer for alpha. And if you make crisscross, alpha is, as I said before, alpha is what? The coefficient of linear expansion for a solid, and this is represented per Kelvin. And if you make crisscross, change in L becomes alpha here, alpha times LC times what? Change in temperature. So the increase in length, change in L is the increase in length. Finally, the increase in length, change in L becomes alpha LC times change in T. Therefore, how much the substance or the rod is increased is calculated by this equation. And if you are asked to calculate length at hot, that means the total length after it is heated, you must use this equation. The second one, before that, the linear expansion coefficient of solid. Some are given here. For aluminum we have 2.3 times, here we have this all is expressed in terms of 10 to the power of -5 per Kelvin. Therefore 2.3 times 10 to the power of -5 per Kelvin, and this one is also times 10 to the power of -5 per Kelvin, and this one is also times 10 to the power of -5 per Kelvin, times 10 to the power of -5 per Kelvin, and this one is also times 10 to the power of -5 per Kelvin. And these all are some values of expansion coefficient of some solid materials. And the definition of this expansion coefficient is when 1 meter rod, iron rod, is expanded by 1.1 times 10 to the power of 5, because iron is 1.1 times 10 to the power of -5 per meter for every 1 Kelvin rise in temperature. That means if the temperature of the iron increases by 1 Kelvin, the substance will increase by this value, that means 1.1 times 10 to the power of -5. Therefore this expansion coefficient indicates per Kelvin how much the substance is increased. And the second one is surface or areal expansion. In this areal expansion we have two areas, that is AC, that means area at cold, and AH, area at hot. And the difference of the two is the increase in area. Because of change in temperature, that is, as I said before, change in temperature is always TH minus TC. Therefore, if you see diagrammatically, this one is before it's heated up, and this one is temperature at TC, and this one is after it is heated, it is TH. Therefore for this we use fractional increase, and the fractional increase in all cases it is similar. Therefore change in A over AC, and fractional increase, that is beta, that means the fractional increase per area in surface area, the fractional increase in surface area divided by change in temperature, that is fractional increase over change in T is beta. Beta is the area expansion coefficient. Therefore this one becomes change in A over AC the whole over change in T. And finally we got this, and rearranging this or making crisscross, we got this value. Change in A is equivalent to beta AC times change in T, and this value or this equation is used to calculate the increase in area of areal expansion. And if you are asked to calculate area at hot temperature, you must use this equation, the second equation, that is A at hot is equal to AC into 1 plus beta times change in temperature, and beta and alpha have a relation. To get the relation between beta and alpha, we will start from the equation of this. That means beta is equal to change in A over AC times change in T, and as you know, change in A is AH minus change in A is AH minus AC. Therefore, you will substitute AH minus AC in the place of change in A divided by AC times change in T, and making crisscross, this one is multiplied by this. Therefore, beta AC change in T becomes is equal to AH minus AC, and shifting AC to the right, here we shift this AC to this direction, and we have left with only AH. Therefore, AH becomes beta AC times change in T plus AC, and let us take AC as a common. When you take AC as a common, 1 plus beta times change in T becomes, and L is length, and this length square is always what? Area. And length at, if it is length at hot, this area becomes area at hot, and length at cold square becomes area at cold. Therefore, taking this relationship, area at hot is equal to length at hot square, and therefore we'll substitute in the place of this, or we will take LH is equal to LC plus alpha LC times change in T. This one is the equation we derived before to use to calculate the length of hot rod, and squaring this, we square this and this whole we got by squaring these two. LH square is equal to this square, and finally LC the whole square is equivalent to LC the whole square 1 plus this and this, and this part as we see before, alpha is expressed in terms of 10 to the power of -5. Therefore, when it becomes a square, its value decreases by large amount. It becomes 10 to the power of -10 scale. Therefore, since it is 10 to the power of -10, it's much smaller, and we take this as approximately 0, and we left with LC the whole square into 1 plus twice of alpha change in T, and LC square is A. Therefore, we will substitute in the place of LC square AC and twice of alpha change in T, and this one is considered as approximately 0, as I told you before. And finally we get AH is equal to AC 1 plus twice of alpha change in T, but we derive for AH is equal to AC into 1 plus beta times change in T. If you compare these two equations, beta and twice of alpha becomes what? Similar or equivalent. Therefore, we can generalize that. From these two equations here. AC 1 plus twice of alpha and beta and change in T. Therefore, beta and twice of alpha is what? Equivalent. Therefore, the relation between beta and alpha is beta is equivalent to twice of alpha. Therefore, if you are asked to calculate areal expansion, and if the expansion coefficient given is the linear expansion coefficient, by multiplying by 2, you can take as the areal expansion of solid. And the other thing is, let us take one example for length expansion. We have some brass, and this brass is 50 centimeter long, and the rod is heated from 25 degrees Celsius to 70 degrees Celsius. Therefore, here we are asked to calculate what? The increase in length. That means changing L, change in L, and change in L is calculated by using what? Alpha LC times change in T. Alpha LC times change in T. Since it is brass, for brass it's known, we will take that, and LC is 50 centimeter, and change in T is 70 minus 25. Let us substitute this. Let us substitute it. LC is 0.5. That means 50 centimeter mean that 0.5, and change in T is 70 degrees Celsius minus 25, and we get 45 degrees Celsius. And change in L becomes this one. This value is the expansion coefficient of what? Brass. Linear expansion coefficient of brass. We substitute. This is alpha, and this one is LC, and this one is change in temperature. And multiplying this all, here we cancel out Kelvin by degree Celsius, because degree Celsius is change. Since it is change in Kelvin, and Celsius is what? Similar, as we said before in in lesson 4. No, in lesson 3. Therefore, since it is equivalent, we can cancel out degree Celsius by degree Kelvin, since it is change. And when you multiply this all, you got that 4.3 times 10 to the power of minus 4 meter. And this one is the expanded amount, or increased because of this change in temperature from 25 to 70 degrees Celsius. This brass increases by this amount. And another example, calculate the length of iron rail at 400 degrees Celsius when it's exactly 100 meter long at 200 degrees Celsius. Here, this one is T, H, and this one is what? TC. And this one is L, C. At 200 degrees Celsius, the length is 100 meter. At 400 degrees Celsius, the length becomes how much? That means you are asked to calculate what? L, H. And to do this, change in L is alpha times LC times change in T. And from this, you must first calculate LC is given, and change in T is given. Change in T is because 400 minus 200, it becomes 200, and we substitute alpha LC and change in T, and the product of these three becomes 0.22 meter. And we are asked to calculate what? LH, and LH is from the equation that change in L is equal to LH minus LC. If you shift LC to the left, LH becomes change in L plus LC. Therefore, we got change in L 0.22, and LC is how much? 100. Therefore, the sum of the two gives us LH, and 100 plus 0.22 is equivalent to 100.22 is the length of the substance at 400 degrees Celsius. This is all about today. Until next time, see you.